Okay, so again, a lot of this is being outsourced to those videos on the Canvas page, and we even have these Unit 5 reference posters. I think they do a really good job of just giving you a quick visual, and sometimes just the visual is way more helpful than kind of reading a definition. So the law of large numbers, the complement, addition, and multiplication rules, those have some really nice visuals to help you understand those really well. There's some other things like the general addition and general multiplication rule. We're going to talk about those later. But for now, if you just focus on these and kind of the earlier stuff there, those reference posters can help you quite a bit. I'm not necessarily going to run through these in class today. Just very briefly, we'll talk about some of those concepts. I'm going to focus on the idea of mutually exclusive and independent, because those are kind of the more complicated ideas. All right, so make sure you reference those. Make sure you watch those videos so you can get a really good foundation. And before we jump into this, the idea is tomorrow, we're kind of getting all of the basic overview of chapter 14 done today. Tomorrow, we're going to spend more time looking at actual problems, really working through all the little nuances associated with calculating probabilities. Okay, so probability terms. The big one here, empirical probability, is probability that comes from observation or experiment. And so here's an example. Flag High's girls soccer team seems to win 90% of their games. Therefore, the empirical probability of them winning is 90%. All right. The theoretical probability is something that comes from a model and calculations, I guess you could say. So something like this. Okay, well, here we go. The probability of drawing the ace of spades from a full deck is 1 in 52. I didn't sit there and experiment to figure out what that probability is. I just told myself there's 52 cards. I'm looking for one specific card. There's 1 in 52 probability I'm going to get it. Pretty straightforward idea, but that theoretical probability versus empirical probability, that'll be a big distinction, and we'll talk about that a little. We'll do some problems using those two different types tomorrow. The third type here, this is your personal probability. And this is your own subjective assessment for how likely something is to happen. So you might be 100% sure you're going to ace the probability exam. And I bet all of you are feeling that right now. So that's a subjective personal probability. So I'm sure you're correct, and you probably will ace that test. Okay. The sample space. This is the collection of all possible outcome values. So the sample space for a coin flip is just heads and tails. It doesn't matter how many times you flip a coin, the only possible outcomes are heads and tails. The sample space for suits in a deck of cards is hearts, diamonds, spades, clubs. It doesn't matter how many cards we draw. These are the only 4 outcomes. So there we go. If you can enumerate and all of the different outcomes, that's your sample space. Okay, so we've got some notation here. We're going to signify what all this means. This right here is just the probability of event A happening. So P of A. It looks like a function from algebra, but of course, we're talking about probability. The probability of event A and event B happening is given this way. So this is called and, it's called intersection, it has a couple different names. So that symbol, when it looks like that, is an intersection. It means and. It's equivalent of that word and. This other one is equivalent of the word or. So we're saying the probability of event A or event B happening. And this one is easier to remember. The other word for this is union. So you can see that's a U, union. So that might help you keep it straight, which one is which. And it's important to recognize the difference between those two, because a lot of times it'll just be given in this kind of probability notation, no other information given. The probability of an event A not happening is given like this. You put this superscript C, and that means it's the complement of it. And so that is quite literally, and this is in your book, so hopefully you've already read this, but it's quite literally 1 minus the probability of event A happening. We're not really looking at this today. I just wanted you to be aware of the notation for this. Okay, and we will definitely use this a heck of a lot more. So properties of probability. All probabilities must be between 0 and 1. And a probability of 0 means that the event is impossible. 1 means it's a certainty. And they can be expressed as decimals, fractions, or percents. This isn't like your coefficient of determination or your correlation. You know, those need to be presented specific ways. This, you know, you might see it presented lots of different formats. All right, there are some other things I didn't define, like event and outcomes and trials and stuff like that. That's all in your chapter. You can kind of read through that. Okay, so no units when we're talking about probability. It's just straight up what percent chance is it to happen. The combined probabilities of all outcomes in the sample space must add up to 1. So the example here is, like we talked about before, there is sure a 1 in 52 probability of drawing any particular card in its standard 52 card deck. But if I have 52 cards, each with a 1 in 52 probability of being drawn, I add it all up, that has to add up to 1, and it does. And there we go. Not a pretty straightforward idea. So that's all the preliminary stuff. A little more of the big picture is given in those videos that I want you guys to watch later. Mutually exclusive. We're going to spend a little bit of time on this today. This is one that is conceptually really simple, but in practice it can be a little bit more confusing sometimes. And you might have noticed that in statistics, it happens that way. So mutually exclusive. Two events are mutually exclusive if they cannot both occur. So let's see. And we're going to determine if this is mutually exclusive or not. So 2 dice are independent, and we haven't really talked about that. But the event of rolling a 6 is not mutually exclusive if we roll 2 dice, because you could both have both dice land on the same number. So it's not like only 1 die is allowed to land on 6. Both of them could. All right, so they are not mutually exclusive. A house could have a garage and have air conditioning. They're not mutually exclusive to have one or the other. You can have both of them. So I give you a couple of examples of things that are not mutually exclusive. But here's one that might be pertinent for you guys. College choices. If you're going through a few colleges right now, you're not quite sure which one you're going to attend. Well, eventually you're making a choice, and that event is mutually exclusive. You can't choose to go to U of A and ASU or whatever your choices are. You have to pick one. So you can't be a student at both universities, generally speaking. I think it's fair to just generalize it that way. Okay, another name for this is disjoint. There's nothing different between these two terms. They're just both used. So you need to be aware that they mean the same thing. And here's kind of the litmus test you're kind of asking in your test, in your head, when you're looking at a scenario. So ask, is it possible for the second event to occur if the first event occurs? Can they even coexist? And if the answer is no, then they are mutually exclusive. Okay, so conceptually, not that bad. And if you do have any questions, you can chat them at me, anything like that. Raise your hand. So now we're going to look at this mathematically. We're still looking at mutually exclusive. So there's 2 ways we can think about it. So the probability of event A happening and event B must be 0 if they are mutually exclusive. Disjoint events can't both happen. So therefore, we know that the probability of A and B happening must be 0. So here we have the probability of attending ASU and attending U of A is 0. The probability of a coin landing on heads and that same coin landing on tails is 0. the probability of acing your next stats test and failing it at the same time is 0. So it starts off pretty straightforward. Hopefully I can give you guys some more examples in the next few days so that you can really test that, because like I was saying, conceptually it's pretty straightforward, but in practice sometimes it's a little harder to tell the difference. So we do have a mathematical test right here, and we'll see how we might use this test. Probability of A and B must be 0. But here's another thing we can do, and this is again still mutually exclusive. So the probability of A or B happening must be the same as the probability of A plus B happening. And this is what we call the addition rule. So A plus B, the probability of A plus the probability of B equals the probability of A or B. But this is only true if the events are mutually exclusive. Okay, so this is a key criterion that must be met. So here's how we can use this. We can use this in reverse. So let's say that we already know the probability of A or B happening. We know the probability of A, and we know the probability of B. If we know these three numbers, we can just plug them into this formula. If it all checks out, then they're mutually exclusive. If it doesn't check out, then they are not mutually exclusive. And we're going to do an example of this. I just wanted to make sure that idea is clear. So we're using a rule we have that has a specific criterion that they must be mutually exclusive for this to be true. And then we're going to use that to test if two events are mutually exclusive. Okay, so if that's clear enough, here's our example. The probability of someone taking calculus at Flag High is 0.04. The probability of someone taking statistics at Flag High is 0.05. The probability of someone taking statistics or calculus at Flag High is 0.08. All right, so if we've got the probability of both happening is 0.08, I'm going to plug that in, 0.08. I'm going to plug that in for this value right here. And it doesn't matter which one's A or B, I'll call A calculus. So the probability that someone's taking calculus is 0.04. And the probability that someone is taking statistics is 0.05. So if I have those three numbers and I plug it in, I see 0.08 equals 0.09. Well, okay, obviously not true. So are these mutually exclusive?
Yes.
Right. And remember, it's kind of a counterintuitive thing. This is why you might need to kind of look at it a few times. But if this is not true, then they are not mutually exclusive. And what does that mean in practice for this problem? It means this. Someone taking calculus could simultaneously be taking statistics. It's not usual. It could happen, and I don't know if that's true of anyone in this class. So therefore, because both events can occur, they are not mutually exclusive. And we tested this mathematically with this right here. Had this been 0.08 equals 0.08, we would say they are mutually exclusive. There's no one currently taking calculus who's also taking statistics, but we see that's not true. Are there questions on this scenario? That question, that problem? Okay. And your homework tonight is a worksheet that has more problems like this. So hopefully by the time you're done, and hopefully by the time you're done with it, it's making more sense and you're feeling a little more comfortable with that concept. Independence, okay. So independence, we talked about this to some degree, but in probability, it means that the outcome of one event has no effect on the, and I should add something here, the probability of the outcome of another event. So probability, one event happening has no effect on the probability of another. Okay, so again, going back to dice, those are a very clear example of things being independent, because no matter what I roll on the first die, it does not affect what I will roll on the other. On the flip side, you might, be picking out what clothes you're wearing tomorrow. Those are not independent, because basically if you're trying to match, your shirt will depend on maybe your shoes or your pants or your jacket or whatever other clothes. You might want it all to match. So it's not independent. Maybe for you, it is all independent and you just look fabulous every day. Okay, but let's assume that there's some kind of coordination going on, so therefore it's not independent. So does the first event happening change the probability of the second event happening? And that's a question to ask yourself to determine if this is, if the events are independent. Okay, so if the probabilities do not change, then the events are independent. Okay, and again, mathematically, we have something we can use, the multiplication rule. Okay, so this multiplication rule, we use it for other purposes, but here we're using it as a test. It says that the probability of event A times the probability of event B equals the probability of events A and B happening, but this is only if they are independent. And again, just like we did with mutually exclusive, because this is a criteria for this to be true, we can go and examine data. And we could say, if this checks out for our data, then the events are independent. If this does not check out for our data, then they are not independent. Okay, and there, that's basically saying what I just said. All right, so conceptually, are there questions on this? And all right. Again, questions can come up. You can stick around if something isn't clear and we can come back to it. All right, so I kept the formula up here, the equation. So probability of A and B has to equal probability of A times the probability of B if these two events are independent, if they're independent. So here we go. The probability of a car having problems with the transmission is 1 in 75. The probability of a car having problems with the radiator is 1 in 25. The probability of a car having problems with the transmission and the radiator is 1 in 100. Are these independent? Are the first two independent? So again, we can just kind of plug this in. I've got both happening as a 1 in 100 probability. You could convert this to decimals or percents or whatever you want if you'd like. Transmission, I'll call this event A, is a 1 in 75 chance. Radiator is a 1 in 25. I'll call that B. So basically, I want to multiply these together. And hopefully you can tell they're not going to be equal, but I'll just go ahead and figure out what that is. So if I multiply on the left, I get 1 over 100 equals 1 over 1,875. Obviously not equal. This equation is only true if they are independent. Since it's not true, that means these two are not independent. So what does that mean in context? It means that if you have problems, for example, with your transmission, that increases the probability of having problems with your radiator, and vice versa. So if these were truly independent, then having both be a problem would be equal to just those two probabilities multiplied. But because it happens at a 1 to 100 probability, it looks like having problems with one is going to lead to problems with the other. They are related in some way. Okay, so conceptually and mathematically, are these two ideas making sense for today? You can give thumbs up if you're feeling good or anything like that. And again, doesn't have to be 100% there today. The idea is that tomorrow we will do some more practice with this, but hopefully with the practice that I give you tonight, you're gonna feel pretty decent about it. All right, and here's this again. If you haven't read chapter 14, please do so. That'll help bring everything together. There's a couple of videos, like I keep saying, on the Canvas page. It is expected that you guys go and watch those. And then the worksheet that's posted there on the assignment, it tells you which ones you need to submit for the text box online. So anyways, take care of that. If you have questions or anything else, you can stick around. And besides that, have a wonderful day.